the potential well into which information in the form of electrons is stored. So you are literally storing information in the form of electron. So 10-volt equivalent information in the form of electron is stored in this depletion layer. For example, I'm saying if I give 10 volt, you say 100 electrons are produced. So 100 electrons are stored here in the depletion region. They cannot move anywhere because they are bound by the depletion region of the device where the depletion region is formed. You have a p-type silicon substrate on which you're going to grow this device, right? And they cannot escape above also because you have an isolating SiO2 layer. So you cannot, the electrons will be permanently stuck inside this depletion region only. They cannot come out of the depletion region. Okay. So during the second phase, what happens? I am going to give G2 to 15 volt to produce a deeper well as shown in the figure. See, first case you see, for G1 I am giving 10 volt, for G2 I am giving 0. So only depletion region is present inside G1 only, and below G2 nothing is there. Now you see I am giving 15 volt to G2. So there exists a potential difference, and you have a deeper depletion region. So when you have a deeper depletion region, electrons from the adjacent electrode, they will go to the adjacent well. So in this way, you see I have transferred the information from G1 to G2. So I have transferred the electrons from G1 to G2. Now, if I don't want this electrons to move away, so what should I do? I should give a voltage plus 10 volt and 15 volt here so that the stored electrons cannot come out. Okay, so that is the logic. So the stored charge then transfers into the deeper potential by diffusing down the potential gradient, which can be a slow process. So you are creating a charge gradient here. Here you have a lot of electrons. Here you have no electrons. Just like diffusion current, we have seen diffusion current, right? Diffusion current flows because of difference in concentration. Below G1 you see you find lot of electrons, and below G2 you find no electrons. So electrons tend to go and occupy the empty spaces. So the electrons will try to go and occupy the empty spaces below the G2. In order to ensure charge transfer, potential wells must physically overlap. Yes. So the charge transfer, see here, can happen from one device to another device only when there is a continuity or the electrons have a path to move from G1 to G2. If electrons don't have a path, then there is no use in having these charge coupling devices. Or either the path should be continuous or the path should be overlapping. Only in such cases, I can ensure charge transfer to happen. As the depletion layers are only a few micrometer deep, the spacing between the neighboring gates must be as small as possible to ensure sufficient overlap. See what we are seeing here, it will not be as deep as what you see here. It will be in the order of micrometers. So you have to carefully fabricate all these devices to ensure that electrons are being transferred from one well to another well. So now that you can see the charge is completely moved to G2, and the voltage is G1 is reduced to a lower value and G2 is set to a higher value. Now you see G1 is given G2 is given 10 and G1 is given 15. Okay, so the value is being, sorry, it is not 15, it is 5. So G1 is given 5 volt and G2 is given 10 volt. Now the charges are completely moved under G2. Now I want to make a third transfer. So now if I want to make the voltage if I want to transfer the charges from G2 to G3, so I will give a higher voltage to G3 because G2 is already at 10. So only if I give a higher voltage to G3, you will get a deeper well so that these electrons can move from this well to the deeper well. So now you see a third phase transfers a plus 15 voltage pulse to the next gate, and the charge is transferred fully from G2 to G3. After charge transfer takes place, you have to stabilize the voltage. So G3 will be made 10, G1, G2 will be made 5 so that these charge electrons will not escape from the potential well. So you can even apply other voltages to G4, G5 so that you can keep on move the electrons from one place to another place. So voltages on G2 and G3 can be relaxed. You have to complete one cycle of clock frequency. The charge has been transferred from G1 to G3 in one cycle of clock pulse. So one cycle of clock pulse includes what voltages I'm going to give: 15, 10, 5, and 15 to apply to each gate electrode. So if I apply these voltages to each of the gates, I'm going to have a charge transfer from G1 to G3. And this one complete charge transfer cycle from G1 to G3 is called as one clock period. So one clock cycle means I'm going to transfer the contents completely from G1 to G3 by applying specific voltages as we have discussed. So initially G1 is 10 and I'm not applying G2 anything. Then I'm applying G2 is 15. So G1 is 10, G2 is 15. Then G2 is made 10 and G1 is made 5 so that the electrons don't escape. For a third transfer, G3 is given 15. And after the electrons are completely transferred, G3 is made 10 and G1 and G2 are made 5. Okay, so these are the specific DC voltages you are going to give as input to the gate electrodes to facilitate electron movement from G1 to G3. See, everything is depend on how charges or electrons are moving from one potential well to another potential well. That is why it is called as charge coupled devices. And what we are seeing is a charge transfer device. So the CCDs come under charge transfer devices. Okay, they are going to transfer the electrons from one potential well to another potential well. How the transfer takes place? Just by giving a higher voltage than the previous potential well, you create a deeper well, and because of charge gradient, these electrons will get transferred from that potential well to the next potential